This is part 2 of my lecture on stellar evolution and stellar remnants. The most common type of stellar remnant is a white dwarf because they're the dead cores of low-mass stars like the Sun, which are much more common than high-mass stars. The core of the Sun contains a third of its mass. By the time the outer parts are expelled when the Sun dies, the core would have shrunk to around the size of the Earth. That's a huge mass in a tiny volume. Once it's exposed to space, it cools quickly from millions of degrees to tens of thousands of degrees. Remember, white dwarfs are at the bottom left of the HR diagram. They're hot, but tiny. The first white dwarf discovered is shown here. It's one of the two stars, which together we see as Sirius, the brightest star in the night sky. This is an X-ray image. The white dwarf is the one at the bottom, which looks brighter because it's much hotter than its main sequence companion. In visible light, the main sequence star is much brighter because it's larger. The physics which explains what keeps white dwarfs stable is quite complicated. Normal gas pressure cannot support such a dense object from collapsing under its own gravity. But in white dwarfs, a different type of pressure is produced called electron degeneracy pressure. The man who first figured this out was Subrahmanyam Chandrasekhar. That's a difficult name for Americans to pronounce, but where I come from in the southeastern part of India, this name is about as common as John Smith. Chandrasekhar finished his bachelor's there and received a Government of India scholarship to study in Cambridge, England. On his journey by ship to England in 1930, Chandrasekhar came up with what would eventually earn him the Nobel Prize and get a space telescope named after him. He applied principles of quantum physics and relativity to the dense cores of stars. The quantum in quantum physics refers to the fact that on the smallest scales, things that seem continuous to us, like light and energy, actually come in discrete quantities. As you've already learned, one quantum of light is called a photon. For electrons and some other particles, only two particles can occupy the lowest energy state. The next few would need to have more energy, and as you pack more and more into a tiny volume of space, you would end up with higher and higher energies. This means these electrons are traveling faster and faster. This produces a special kind of pressure called degeneracy pressure, which helps support white dwarfs against gravitational collapse. Chandrasekhar realized that white dwarfs are so dense that the electrons must be moving close to the speed of light. At 1.4 times the mass of the Sun, they would exceed the speed of light, which is forbidden according to relativity. So there should be no white dwarfs that are more than 1.4 times the mass of the Sun. This is referred to as the Chandrasekhar limit. Chandra finished his PhD at Cambridge in just 3 years and then stayed there on a fellowship. But at one point, one of the top astrophysicists at Cambridge, Arthur Eddington, publicly ridiculed him on the concept of the Chandrasekhar limit. Chandra was deeply offended and decided to leave England. He moved to Chicago and stayed here until he died in 1995. He contributed greatly to several fields of astrophysics, but in 1993 was awarded the Nobel Prize for the limit that's now named after him, which he came up with way back in 1930. One of the strange things about white dwarfs is that more massive ones are smaller. One that's got as much mass as the Sun is about as large as the Earth. More massive ones are even smaller. White dwarfs remain stable as long as they don't exceed the Chandrasekhar limit. They just sit there and slowly cool off. By the way, white dwarfs aren't white. While we're renaming planetary nebulae, we could also rename white dwarfs to dead sun cores or something else. Young white dwarfs appear blue and older ones appear green or yellow. It would take tens of billions of years for a white dwarf to cool so much that it would appear red. Since the universe itself is less than 14 billion years old, there are no red white dwarfs yet. How amazing is that? Things get a lot more interesting if a white dwarf has a close companion. Material from the companion can spill onto the white dwarf and form what is known as an accretion disk. Accretion is when matter comes together due to gravity. As the gas spirals inward, it gets hotter and hotter. This gas is made of hydrogen because it comes from the outer parts of a star. If it hits 10 million degrees, the hydrogen fuses into helium. This, of course, is what happens in the cores of main sequence stars, but in those cases, it's kept contained by the star's outer layers. Here, it's happening outside a white dwarf. The burst of energy from nuclear fusion destroys the accretion disk and makes the binary star system appear much brighter all of a sudden. Astronomers call this a nova because there were times in history when people saw a new star in the sky. That would make a really bright new star a supernova. Of course, the reason for the sudden increase in brightness is completely different for a nova and for a supernova. But remember, things are named according to how they appeared to the people that first discovered them, not according to the actual physical processes that produced them. Here's a link to a simulation of a white dwarf in a binary system before it undergoes a nova outburst. The white dwarf is a small blue object in the center, and you see the accretion disk and the companion star. A nova outburst does not destroy the white dwarf itself, just the accretion disk. So the white dwarf can again strip matter from its companion, forming a new accretion disk, which results in more fusion and a new nova outburst. There are white dwarf binaries that go nova once a year or so. But if too much mass gets dumped onto the white dwarf, it could exceed the Chandrasekhar limit. If that happens, the white dwarf will explode. What do astronomers call this? A supernova. More specifically, a type 1a supernova. Could things get any more confusing? Again, it's all about how they appear to the naked eye or through a small telescope, how they really appear to the people that discovered these things. If you see a new star in the sky and it's not all that bright, maybe it's a nova. If you see a new star in the sky and it's really bright, it's a supernova. Just seeing a bright new star in the sky doesn't tell you what actually made the star appear really bright. Maybe it was the collapsed core of a massive star, or maybe it was the complete explosion of a white dwarf. We need additional observations to tell what actually happened. Let's look at the sequence of events shown in this figure. We start off with two main sequence stars in a binary system. The more massive one turns into a red giant first, and then has its outer parts blown off, revealing a white dwarf. Meanwhile, the companion star evolves and eventually turns into a red giant. Then, some of the gas from the companion can spill onto the white dwarf. If the mass of the white dwarf does not exceed 1.4 times the mass of the Sun, the Chandrasekhar limit, then there'll just be periodic nova episodes. If the mass of the white dwarf does exceed 1.4 times the mass of the Sun, the white dwarf explodes as a type 1a supernova. In summary, a type 1a supernova is a total explosion of a white dwarf in a closed binary system. A type 2 supernova is what you learned about first. It's when a massive star's core collapses once it's made entirely of iron, which releases a huge amount of energy, ripping the outer layers apart. Let's say you see a really bright new star in the sky. It's a supernova. How can you tell which type it is? You can take a spectrum. Remember that in a type 2 supernova, it's the outer layers of a star that are exploding. The outer layers of a star are made mostly of hydrogen. White dwarfs don't contain hydrogen. They're made of heavier elements like helium and carbon. So if you see hydrogen in the spectrum of a supernova, it has to be a type 2. If you don't see hydrogen, it could be a type 1a. Technically, it could also be a type 1b or 1c, but you don't have to worry about those for this course. Also, remember that massive stars, which produce type 2 supernovae, don't live long. So type 2 supernovae can only be found in galaxies and regions within galaxies that contain young stars. On the other hand, a white dwarf is the dead core of a low-mass star. That star could have spent billions of years on the main sequence before the white dwarf appeared. So type 1a supernovae can be found in old populations of stars. Now let's look at the cores that are left behind after the outer parts of a massive star explode as a type 2 supernova. Remember, the protons and electrons have fused together to make neutrons. This is called a neutron star. Here again is the Crab Nebula, which is the remnant of a star that was seen exploding in the year 1054. If we zoom way in to the center of the nebula with a radio telescope, we can see a spinning object emitting a jet. It's actually spinning 30 times per second, which means it must be incredibly small, about the size of a small city. It's a neutron star. Here's a model. Here's what we think is going on to produce what we see. Just like the Earth, stars have a geographic north and south pole and also a magnetic north and south pole. In the case of the Earth and the Sun, geographic north is close to magnetic north, but this is not always the case. For instance, on both Uranus and Neptune, the geographic pole is tilted from the magnetic pole by 40 to 60 degrees. We think the same thing is going on with the neutron star in the Crab Nebula. Neutron stars have enormously powerful magnetic fields. When you compress a star's core, its magnetic intensity greatly increases. The charged particles that happen to be nearby line up along the poles of the neutron star and produce a different type of light than we've encountered before. It's called cyclotron radiation, or if the charged particles are moving close to the speed of light, then synchrotron radiation. Now the important thing, again, is that the magnetic pole is not aligned with the geographic pole. So each time the star spins, the magnetic poles could point directly towards the Earth. Since there's a bright beam of light coming from the magnetic poles, we see a bright flash at this time. This is called a pulsar. All pulsars are neutron stars. We may not see a neutron star as a pulsar if the alignment is not right. For instance, if the magnetic poles are close to the geographic poles, the beams will either never point towards the Earth or always point towards the Earth. Also, the beam of light carries away a lot of the neutron star's magnetic energy. Over time, the magnetic field weakens and the beams fade away. So old neutron stars are also not pulsars. Only young ones that are aligned the right way are pulsars. Just like white dwarfs can have close companions, so can neutron stars. So here also, gas from the companion can be dumped onto the neutron star, forming an accretion disk. Since a neutron star is a lot smaller than a white dwarf, the gas has further to fall, so it can get much hotter. It can fuse hydrogen into helium, and even helium into carbon. This produces a burst of not just visible light, but also X-rays. Rather than also referring to these as novae, or novae, astronomers call them X-ray binaries. And just like white dwarfs, neutron stars also have a maximum mass. It's the same physics that we learned about when we were studying neutron stars. It's the same physics we saw when we encountered white dwarfs. Neutrons, just like electrons, also need to occupy higher and higher energy states as they get packed tightly. This is neutron degeneracy pressure. At 3 times the mass of the Sun, the neutrons have to move at the speed of light, which again is forbidden. In this case, the neutron star doesn't explode, it collapses in on itself, forming a black hole. Chandrasekhar's fusion of quantum physics, relativity, and stellar interiors paved the way, not just for understanding of white dwarfs, but also neutron stars and black holes.